This is the Gaia Space Telescope. As you can see at the top there, it had a 5-year mission to map 1 billion stars. It did that so well, they decided to change its mission to a 10-year mission to map 2 billion stars. So, what am I talking about? Why map the stars in the Milky Way? How do you map the stars in the Milky Way? What type of data can you get? And what do we learn from all the data that Gaia has been producing? So first start with the why. Why do we want to map the stars in the first place? Well, it's not just a question of saying, I want to know where the stars are for a star atlas. And for that, well, we just want to know where things are so that we can find them again later, or we can tell if things have moved, or we can tell if a new object has appeared. But mapping the stars goes beyond just wanting to make a good atlas. If we can determine the positions of the stars accurately enough in the three-dimensional sense, in other words, where are the stars in the Milky Way, rather than simply where are the stars in the sky, then we can gain a much better understanding of the structure and the evolution and ultimately the history of our own Milky Way galaxy. So how do we map the sky? Is it simply a question of, well, take a lot of pictures and stitch them together? Well, that approach, of course, works fine for the Earth. We can use satellites to photograph the surface of the Earth, stitch them all together. We've got basically a map of the entire surface of the Earth. But that doesn't work so well for the stars in the sky because, well, problem number one, the stars move. Nothing in the galaxy is static, and therefore we can't simply take pictures and stitch them all together. Problem number two is the stars are all at different distances. So even if we could get a nice two-dimensional picture of the sky, it doesn't give us three-dimensional data. Knowing simply where they are in order to plot them on a star atlas is not enough to tell us what the galaxy is doing in terms of where are the stars and how are they moving. If you think, for instance, of the familiar Orion constellation, we see it as a particular pattern of stars in our sky, but in fact all of those stars are at different distances from the Earth. And it's only by knowing those distances we can get a proper three-dimensional map of what the stars are actually doing in our galaxy. And being able to determine the distances is not only important in order to get a three-dimensional picture to understand the full structure of our Milky Way galaxy, it's also rather important for understanding the stars themselves. Because if we think about plotting stars in the familiar diagram I've shown on the right-hand side, where we plot the luminosity of the star on the vertical axis and the colour or the surface temperature of the star on the horizontal axis, well, okay, without knowing the distance, how do we know how luminous a star is? If we see a star in the sky, how do we know whether or not it's a very bright star a long, long way away, or whether it's a rather dim star rather close to us? If we don't know the distance, then we don't know the luminosity, and therefore we don't know where on this diagram it is. For instance, if we had a blue star, well, a blue star could in principle be a blue supergiant or a main sequence star or something like a white dwarf. If we don't know the luminosity, we don't know what type of star it is. Similarly, if we look at a red star, how do we know if that red star is a supergiant or whether it's a red giant or whether it's a red dwarf? Yes, we can get some clues from the spectrum of the star, but in principle, if we don't know the distance, then we can't determine absolutely its luminosity. And if we don't know its luminosity and its surface temperature, we don't know where on this diagram it is, so we don't know what type of star we're dealing with. And bear in mind also, as a sort of an aside, if we don't know the type of star that we're looking at, we also don't really know much about any exoplanets that could be orbiting that star. Because when we look for planets around other stars, we always measure the mass of the planet relative to the mass of its host star, or the size of the planet relative to the size of its host star. So if we don't know much about the host star, then really we don't know much about the exoplanets either. So understanding distance is critical to understand the nature of the stars and the three-dimensional picture of how our Milky Way is put together. How do we get distance? Well, we can get distance from the familiar idea of parallax, the apparent change in the position of an object due to the motion of the Earth around the Sun, as indicated by this diagram on the right-hand side. As the Earth goes round the Sun, a nearby star will appear to move relative to more distant stars. And diagrams like this always imply that a nearby star can be aligned with more distant fixed stars to determine the parallax angle. And by parallax angle, I mean that angle there. You can see the parallax angle is going to be very small if the stars are a long way away compared to the distance from the Earth to the Sun, which is of course the case. The distance from the Earth to the Sun is 150 million kilometers, but the stars are, generally speaking, light years or tens or hundreds of light years distance. So that parallax angle is a very small angle. But it's not simply a question of seeing how nearby stars move, apparently, compared to more fixed stars, because all the stars in the sky will appear to move as the Earth orbits the Sun. There's no such thing as a fixed star. Some stars are close, some stars are more distant, but they will all appear to move. And if we think about the actual size of the angle, remember that about 3 light years would give us a parallax angle of 1 arc second. Remember, an arc second being 1/60th of an arc minute, which is itself 1/60th of a degree. So even a nearby star at 3 light years would have a parallax angle of 1 arc second. And that distance is known as a parallax second, usually abbreviated to a parsec. So 1 parsec is a little bit more than 3 light years when we work out the angles there in that triangle as shown. Of course, no stars are that close. The nearest star is about 4 light years away, or a little more than 1 parsec. And when we're talking about the size of the galaxy being tens of kiloparsecs in size, of course, most of the stars in the galaxy will have very, very small parallax angles. And that is the crux of the problem. To calculate distances, we need parallax. For parallax, we need to know the star's actual position in the sky. Knowing its position relative to other stars doesn't help. If all the stars will appear to move as the Earth orbits the Sun, then simply knowing the position of one star relative to its neighbour doesn't really help us. And the stars themselves are also moving. It's not just the fact that they appear to move because of the Earth's motion. If we imagine freezing the Earth and watching the stars, all the stars are orbiting the centre of the Milky Way, and so over time periods of years or tens of years or hundreds of years, they will all be moving in their own right. This is why mapping the stars in the Milky Way is not a trivial task, and that is why it's taken, if you like, until now for us to do this with the sort of precision that Gaia is able to give us. It is not a simple task to simply work out where the stars are. So let's think about how we can map the stars accurately. This is a little cartoon that just reminds us what the sky actually looks like. Okay, we don't see the stars move that much because when we look at the stars, even through a telescope, they don't appear to move much from night to night or even year to year. But if we were to look with sufficient precision, we would notice that all the stars are moving because of the motion of the Earth around the Sun. Here, some red circles just makes it easier to see that some stars don't appear to move much, and some stars appear to move a great deal. It's all a question of their distance. The most distant stars will not appear to move much as the Earth moves around the Sun. The closer stars will appear to move a quite considerable distance. So how can we tell which stars are actually moving when they all appear to be moving relative to each other? To untangle this idea of the apparent motion due to parallax and the actual motion, called the proper motion, as stars move within the Milky Way itself, we need at least 2 things. We need very high precision measurements. Remember, all of these movements on the sky are going to be very small. And we need a fixed coordinate system because all the stars move relative to other stars. So we have to figure out a way of measuring the position of a star relative to something which we could consider to be fixed. The high precision, or arguably the very high precision, is required because the parallax angles are so small. We would never get a parallax angle as big as 1 arcsecond, which is itself a very small angle. And for a lot of what we're talking about, we'll be talking about parallax angles of a tiny, tiny fraction of an arcsecond. And because both the Earth is in motion and the stars are in motion, we need to think about having a fixed coordinate system. Just as an aside, there were plans back in the 1980s to try and make the parallax angles bigger, not by bringing the stars any closer, which of course is impossible, but we could increase the size of the baseline we use for our triangle to try and get the motion of nearby stars. And there were plans to say, let's not work out the parallax angle over 1 astronomical unit, the distance from the Sun to the Earth. Let's send a spacecraft out 1,000 astronomical units, so the baseline of our triangle is now 1,000 times bigger. That'll make it easier to measure small angles. Well, an interesting idea, but flying a spacecraft out to 1,000 AU, it was calculated, would take about 50 years. In other words, even if they had done that in the 1980s, we'd still be waiting for it to get there. So that never actually happened. So what coordinate systems should we use to map the stars, bearing in mind that we need very high accuracy and we need a fixed coordinate system? Now, I'm sure a lot of amateur astronomers are familiar with the idea of the equatorial coordinate system, in which we refer to the coordinate of a star in terms of right ascension and declination, which are analogous to the longitude and latitude of a place on the surface of the Earth. And that's because we use effectively the pole of the Earth and the equator of the Earth as a reference. Right ascension and declination have been used in star atlases since the days of the first Astronomer Royal. So why are they not good enough for mapping the stars for the sort of precision that we are interested in? If we think of a star atlas like this, the stars are all positioned relative to a coordinate system of right ascension and declination. So if we were interested in the coordinates of any of these stars, we could simply read them off from the axes and the grid that we see in the background there. But if you think about star atlases, for instance, here's Norton Star Atlas 1950 and Norton's 2000. These are not the publication dates of the atlas. They are the dates at which the coordinates of the stars are specified or mapped out or printed. And we need to worry about the so-called epoch, the date at which the coordinates are calculated, because the coordinates change. Remember, the coordinates are relative to the pole and equator of the Earth. But the pole and the equator of the Earth are continuously changing due to precession. Over a period of 26,000 years, the pole of the Earth will point to a particular part of the sky and then come back to that part of the sky again. But basically, year by year, month by month, basically day by day, the coordinates, the right ascension and declination coordinates of any object in the night sky will continuously change. So this is not a good coordinate system if we want to define with precision where objects actually are. So if an Earth-based coordinate system is not suitable, what about using the Sun as a reference? Well, actually, that would also lead to small errors because the Sun does actually move. The solar system's centre of mass is not in the middle of the Sun. Because of Jupiter and Saturn and the other planets, the Sun actually moves slightly relative to the centre of the solar system. In this little cartoon, it's slowing down just so that we can see that in 2027, the centre of the solar system will be just inside the surface of the Sun. But for quite a few years, that hasn't been the case. We tend to think of the planets going round the Sun. That's what we usually say. But actually, all of the planets, all of the objects in the solar system, including the Sun itself, actually orbit around the centre of mass of the solar system, called the barycenter. Hence, the best coordinate system to use uses this barycenter as a fixed reference point. Then we don't have to worry. We can calculate how the Earth moves relative to that barycenter, and hence we can work out where the stars are with that as a fixed reference point. If we think about what that actually looks like, if we were to think only of parallax and imagine what the sky actually looks like, if we were to zoom in detail, all the stars would appear to trace out an ellipse in the sky depending on exactly where they are relative to the Earth's orbit. The closer ones will trace out big circles or ellipses. The more distant stars will trace out smaller circles. When we take into account the fact that the stars themselves are actually moving as they go around in the Milky Way, then what we would actually see for the motion of every star is more of a corkscrew. There would be a circular type motion because of the motion of the Earth around the Sun, and there would be the motion of the star as it moves through the Milky Way. And what we would see is one superposed on the other. Circular motion because of the Earth's motion, and something close to linear motion because of the star moving through the Milky Way. So stars don't necessarily move in straight lines, but remember, we're talking about a mission here that lasts 10 years, and it takes an awful long time for a star to go once around the Milky Way, hundreds of millions of years. So to all intents and purposes, over a few years, a star will move in something akin to a straight line. And what we see from Earth is all the stars moving in a sort of corkscrew fashion. The first satellite that attempted to measure all of these corkscrew motions of all the stars in the sky in order to determine how they are moving in the Milky Way and also, their distances. The first satellite to attempt this in the 1990s was called Hipparchus. You can see the acronym at the top there. It was a homage to the Greek astronomer Hipparchus, and they sort of reverse engineered it into an acronym, High Precision Parallax Collecting Satellite. Hipparchus catalogued something like 100,000 stars with a precision of about 1/1000th of an arc second, or 1 milli-arc second, abbreviated to MAS. The faintest stars it could see were about magnitude 12. And the Hipparchus catalogue was used for many years after the early 1990s. For instance, it was used by the Hubble Space Telescope to make sure that the Hubble was pointing in precisely the correct direction. It also produced the colours of various stars and enabled us to get more accurate indications of star types for these 100,000 stars. We are talking about Gaia that came along some 20 years later. Now, Gaia stands for that acronym at the top, but we don't have to worry about that acronym because the Gaia acronym was put together, and then they decided we're not going to use an interferometer to measure our star positions accurately, so that acronym is no longer valid. But by that time, the Gaia name was already in use, and they decided to keep the name even though it's no longer an interferometer. I'll explain how it does take its data shortly. The idea of Gaia was to improve on the work in the 1990s of the Hipparchus satellite. Gaia's mission was to give us the positions of 1 billion stars, not only 100,000 but 1 billion stars, and with a precision of not milli-arc seconds but a precision of tens of micro-arc seconds, where a micro-arc second is 1/1000th of a milli-arc second. So we're getting to the point where we have a precision which is absolutely phenomenal in terms of the technology by which these small angles can be measured. The higher precision means that we can see smaller motions of stars, or if you like, the apparent motions of stars at greater distances. If we say that we can't change the baseline of the distance from the Earth to the Sun, then greater precision with the measurement of the parallax angle means that we can determine distances out to greater distances within the Milky Way. In other words, the Gaia could effectively reach further into the Milky Way than Hipparchus could. It can also see a lot fainter stars, down to magnitude 20. Now, I'm sure this idea of 10 micro arc seconds is something nobody can get their heads around because these angles are so small. So we need an analogy to give us an idea of just what this precision means. Okay, 10 micro arc seconds, the sort of design precision of Gaia, 1/100th of a milliarc second. What is that equivalent to? Well, it's equivalent to measuring with some precision the thickness of a human hair seen from a distance of 1,000 kilometers. So imagine standing in Land's End and looking at a person standing at John O'Groats. We're talking about measuring the position of that person to an accuracy of the width of a human hair. That is the precision with which Gaia can measure the position of a star. And it's with that precision that Gaia is able to produce the data that it does. Okay, that's what we want to do. You could ask, well, can't we do that with any other telescope? Why build a new telescope to do this? Why not use some of the fantastic telescopes that were already around? Why not use, for instance, the Hubble telescope, which has been around since the 1990s? Or more recently, we've had the Chamonix telescope, otherwise known as the Large Synoptic Survey telescope, which is sitting in the Vera Rubin Observatory. Can't we use these fantastic telescopes to do the job that Gaia was doing? Well, if we think of its ability to measure with precision and the number of stars it could possibly measure and how long it would take to do an all-sky survey, well, Hubble certainly has fantastic precision. It could measure the position of a star to better than 1 milliarc second. The Chamonix telescope certainly has the ability to survey billions of stars. That is precisely what it's going to be doing for the next 10 years or so. But the Chamonix telescope doesn't have the precision. It has a precision that's perhaps 100 times worse than the Hubble. And the number of stars that the Hubble has actually measured detailed parallax measurements for is measured perhaps in the thousands rather than in the millions or the billions. So the length of time it might take one of these telescopes to do a survey, well, yes, the Chamonix could do a survey in 10 years, fine. But if we wanted the Hubble to do that with its fantastic high precision, well, the Hubble would take perhaps more than 1,000 years to do that. And that's assuming it only looks at every star once. If you wanted to make measurements of stars multiple times, then it would take many thousands of years to do that. So some telescopes have the ability to do large-scale surveys. Some telescopes have the ability for high precision, but nothing could do both, which is why Gaia was built. So how does Gaia achieve this fantastic precision? Well, the Gaia hardware was put together. It's an ESA project, and it was put together with the hardware from a number of different companies. The optics, for instance, came from Germany, France and Belgium. So the detector came from the UK. Some of the electronic power systems also came from the UK. And then finally it was all integrated by the Astrium company in Toulouse, France. Astrium is a company which was then incorporated into the Airbus consortium. It was constructed between 2006 and 2012 and launched in December of 2013. And it was placed into orbit around L2 in January of 2014. If we remind ourselves about L2, that's one of the Lagrange points. There it is on the right-hand side. It's a point that is sitting 1,000,000 miles above midnight. If we think of the sun over here and the Earth, then of course on the right-hand side of the Earth, as we look at it here, that's the midnight point, because noon is on the left, midnight is on the right. So L2 is sitting 1,000,000 miles, or about 1.5 million kilometers above midnight. And if you sit there and use a sun shield, you can block out the light from the sun and the moon and the Earth all in one go, and it basically gives you an uninterrupted view of half of the sky. And with time, as the Earth orbits the sun, you will then get to see the entire sky. Here's the sun shield itself being deployed under test. So there it is. You can see the scale from the technicians buzzing around it like bees. There it is again. Solar panels on the underneath power the spacecraft. And again from above, we see how it unfurls once it's in orbit. About 10 meters or so in diameter. The sun shield rather important for keeping the entire system, the entire telescope itself, at a stable temperature. It doesn't have to be as cold as, for instance, an infrared telescope like the James Webb, but it does have to be stable temperature in order to get the precision that they are after. So how was micro-arc-second precision achieved? Generally speaking, the larger a mirror, the greater the precision with which you can image, which is why, for instance, we are building the European Extremely Large Telescope in Chile with a 40-meter diameter mirror. But if large mirrors give you greater precision, how do you get this fantastic micro-arc-second precision? Do you need a mirror a few kilometers in diameter? Well, obviously not. From what we've just seen, Gaia is only a few meters or so in size. If we compare the size of various mirrors, here all shown to scale, the largest telescope at the moment is Gran Telescopio Canarias. It will be overtaken before too long by the extremely large telescope shown on the right-hand side. But the space telescopes are shown in the bottom left-hand corner. There they are, or at least some of them. Let me blow that up so you can see it a little more clearly. There's the familiar James Webb in the bottom left and Hubble in the bottom right, and Gaia, you notice, is two mirrors, both of which are rather small compared to Hubble or James Webb. So how do you get this precision with mirrors that are no larger than mirrors in other space telescopes? Well, Gaia achieved its fantastic precision through a rather ingenious combination of the instrumental hardware that was built and a rather novel way of operating. So let's have a look at those. Firstly, the hardware. There's a large detector array comprising close to 1 billion pixels. It's actually made up of over 100 CCD sensors. CCDs are charge-coupled devices. We'll see how they operate shortly. This detector was built by E2V in the UK. And although I describe Gaia as a space telescope, you could say that technically it's two telescopes because it has two sets of mirrors that simultaneously image different patches of the sky. This is a way of reducing the errors rather than measuring the position of one star relative to its neighbour and that star relative to its neighbour and that star relative to its neighbour. All of these errors would then add up. By looking at different patches of the sky simultaneously that are a little bit more than 90 degrees apart, you can minimize the errors of looking at different patches of sky. And the operation is crucial to the way Gaia gets its precision. Both telescopes create star images on the same detector. At first sight, this seems rather odd. Surely if you've got two telescopes, you want two detectors so that you can see the images produced by one and the images produced by the other. No, both telescopes produce images on the same detector array. Not only that, but Gaia spins, and so the star images drift across the detector CCDs. The bottom line is Gaia does not take images. Unlike its cousins, the Hubble Space Telescope or the James Webb Space Telescope, Gaia does not take images. So it's very different to Hubble or James Webb. And it's the way data is read from the CCD that is a crucial element of how it operates and how it gets its precision. Remember, charge-coupled devices, they get that name because light hits the detector, creates electric charge, and then that electric charge is read out as a digital signal, and that number then tells you how much light arrived at each pixel on the detector. And the way you get from, here's a detector array of CCDs? How do we go that from the data that we want that tells us, well, what photons of light arrived in what pixel and when? It's the way the data is read out that makes Gaia different from every other space telescope. And to make sure that we appreciate that, it's worth taking a closer look at how that's done. So firstly, how do space telescopes like Hubble and James Webb work? Imagine a star field, and we can think about how do you build up an image. Remember that an image is really just an array of numbers. And the way that Hubble and James Webb work is they stare at a patch of sky and the light arrives at the sensor and builds up the image. And once the image is complete, after seconds or minutes, then the data is read out. So let's imagine staring at a patch of sky. So this is sometimes called stare mode, because we're going to stare at a patch of sky and then start exposing the CCD. As the photons of light arrive, the image starts to build up. Second by second, minute by minute, we get an image of what we were looking at. Now we're going to read out the data by shuffling all of the pixels through what's called a register and measure each pixel and how bright, in other words, how much charge is stored in each pixel. And then when we've done one row, the next row shuffles down, and then that is pushed through the register and each pixel is recorded. How much charge are we looking at? In other words, how much light produced that particular pixel in the image. It might take a millisecond or so to move a row down, and it might take a microsecond to read out each pixel and convert it into digital numbers. Once the last row has been read out, we now have an array of numbers that corresponds to the amount of light that arrived in each pixel of the image. Of course, it's shown as a 5x5 grid here. In practice, it will be millions of pixels, depending on the particular detector we're talking about. So that's how most cameras work. You open a shutter, you stare at the object you're interested in, you make sure that the telescope stays pointed rigidly, as it were, at that particular target, and then once the exposure is complete, you read all the data out. So that's how Hubble and James Webb work, but that's not how Gaia works. Gaia, remember, is spinning. And if Gaia is spinning, that means the stars are continuously drifting across the CCD. So how does it actually work? Well, if we imagine again what's happening, the stars are drifting across the CCD and the CCD pixels are being read out continuously. So they are always shifting down, just like the star is shifting down. So they stay in sync and the signal keeps adding up. When the star reaches the edge of the CCD, the pixels are read out, and the time at which that star is read out is recorded. There's an atomic clock on board such that it can record precisely the time at which that particular pixel was read. So remember, we're not talking about just following one star. The CCD array will have huge numbers of stars, all of which are drifting down the CCD, and the CCDs are continuously shifting and continuously reading out. And the data that Gaia produces in terms of raw data is the time it takes for a star to reach a particular point in the CCD. It doesn't acquire the image as such. Let's return to this idea of, two telescopes but one detector. What's the point of having two telescopes if those two telescopes are both going to produce stars on the same detector? Well, this is not such a crazy idea because actually that's what happens in sextants. I know you don't probably use sextants that often, I would guess, but if you think about how a sextant actually works, it has a couple of mirrors which will allow you to see not only an object like the horizon, this is what you normally look at through the little telescope, but a star which is at a different position, some many degrees above the horizon. The starlight will reflect off mirrors such that you end up seeing that star in the same field of view. you adjust the mirrors until the star appears to be on the horizon, or if you use the relevant filters, the sun is on the horizon. And that is the angle you're interested in a sextant. And for navigation, it's the altitude of the star above the horizon that's used to determine the observer's latitude. In this case, that's not what we're doing, but it's still light from two objects reflected from mirrors so that they appear in the same detector. In this case, the detector is your eye, and by adjusting the mirrors, you can get the star and the horizon to be hitting the back of your eye, the same detector. And that's what's happening with Gaia. It's using two telescopes at an angle to each other of a little over 100 degrees, and they are producing stars on the same detector. And because we know the angle between those two telescopes, we can work out the positions of one set of stars relative to another set of stars in a completely different patch of sky. That gives us a very accurate way of determining stellar positions. So this is a naked Gaia, if you like. This is what's inside the cylinder that you tend to see. We've got the primary mirror of telescope 1 on the left and the primary mirror of telescope 2 on the right. The mirrors are about 1.5 meters by 0.5 meters. They are much bigger in one direction than the other because we need very high precision in one direction and we're not so fussed about the precision in the other direction. That gives you an idea of the size. These are the Astrium technicians working on the construction. It looks like they are fitting primary mirror number 2 there. The array that we're talking about in the detector comprises a large number of so-called astrometric CCDs. Each of these CCDs is about 5 by 6 centimeters, and the individual pixels on each of those is, as you can see there, rectangular. Again, we need much higher precision in one direction than we need in the other, and therefore the pixels are relatively narrow in one direction compared to the other. These astrometric CCDs are responsible for the timings of exactly when stars hit each of these CCDs. In addition, we have a couple of sets of CCDs on the right there. They're called the sky mappers. These are the ones that are responsible for telling the onboard systems, did these stars come from telescope number 1 or did these stars come from telescope number 2? When the stars have been through the astrometric array, they also go through prisms that tell us how bright is the star in the blue part of the spectrum, how bright is the star in the red part of the spectrum. So even just with these two readings, we can get a pretty good indication of the colour of the star. And some of the starlight also goes through a set of spectrometers that give you the spectra of the star. There are a few other chips in there which are responsible, for instance, for making sure it stays in good focus. And the star drift direction is shown here. It's right to left in this particular graphic. And just to give you a sense of scale, it takes about 4 seconds for a star to drift across one CCD, which contains about 4,000 pixels. Remember, the whole array is about 900 million pixels. So let's think about how Gaia actually operates in practice. Remember, it's spinning. It's spinning about once in 6 hours, but this animation shows everything speeded up so we can see it a little more clearly. There's the two telescopes. They're color-coded just so we can see what's going on. One telescope is looking at one patch of sky, one telescope at another. If we think about what's going on inside there, there's the naked Gaia. Light hits one mirror and then ends up on the sensor at the bottom there, the array of CCDs. So light from one of the telescopes, color-coded blue here, just so we can keep track of it, is shown there. The other telescope is looking at a different patch of sky, but the light ends up arriving at the same detector. But the sky mappers on the right-hand side tell us which telescope we are actually looking at, and so they stay color-coded here. If we follow one star, we don't need to read out all the pixels, we just need to read out the pixels close to the star. Once it's finished one CCD, we've got a reading, then it goes through the next CCD, gets to the end, is read out, and again, the time it takes to do that is recorded, and that is then repeated for all of the CCDs through which the star is drifting. The star then goes through the prisms and we get the amount of blue light and the amount of red light in the star. And for some of the stars, we also get a full spectrum of the star light. So once the star has drifted across this CCD array, which takes approximately a minute or so, we've got multiple readouts of the star brightness. We've got multiple readouts of the time it took the star to reach each of those CCDs, and we've got that very accurately. We've also got an estimate of the star color, and for some of the stars we'll have a star spectrum. Remember, this is happening not for a few dozen. This particular cartoon shows dozens of stars drifting across the array. In practice, there will be millions of stars drifting across the array. And it won't be a question of reading out a star every second. It'll be thousands of stars every second will be read out. And that will be continuing 24/7 for 10 years. Essentially no need for any downtime. So the amount of data, the amount of raw data pouring out of Gaia is huge. And that's why it takes a little while to figure out what this data is actually telling us. Gaia spins roughly once every 6 hours, somewhat faster than the Earth spins, and it's also processing in order to make sure it covers the entire sky. This animation in the bottom right shows the ribbon of sky that Gaia is mapping, and as it slowly orbits around the Sun, because it's at the L2 point which moves with the Earth, it will map out the entire sky over many months and then eventually start remapping the sky. And the darker colours indicates how many times a particular patch of sky has been remapped. Generally speaking, it'll be dozens or hundreds of times over the 10-year lifetime. And what we are showing in the bottom right now is not an image. Remember, Gaia doesn't produce images. It is the data of, if we were to take how many stars does Gaia find and plot them in a map of the galaxy, we find this map in the bottom right. In other words, the brightness of the pixel in this image shows us how many stars Gaia has found in that particular patch of sky. And not surprisingly, it maps out something that we can recognize as being the Milky Way. And in the bottom right-hand side there, also we see the Large and Small Magellanic Clouds. So what data was actually acquired in the 10 years of Gaia running? Well, it started running in 2014 or so. The mission was extended after the original 5 years, and it finished in 2025. There were a number of different data releases, and there are planned for 7. You might think they would number them 1 to 7, but no, they've numbered them 1, 2, E, 3, F, 4, and 5. It takes a little while to take all of the data coming down from Gaia. Remember, it's some colour information, some spectral information, but in terms of the accuracy for positions, it is a lot of very accurate timings that tell us where the stars are. And it takes a little bit of time to convert those timings into precise positions of the stars. And in 2016, the first data release 1, took all of the data from the first year of Gaia's mission and generated effectively a catalogue of millions of stars to the sort of precision that we're talking about. Maybe not quite as good as the final precision that we can expect. Data release 2, a couple of years later, took the first 2 years of data of Gaia's operation and produced accurate positions for not millions, but billions of stars. Scientists were getting rather antsy and were waiting for data release 3, and it was decided to give an early data release to keep these people happy by taking data from the first 3 years of the original mission, and that produced greater accuracy. The precision at first wasn't quite as good as the hoped 10 micro-arc-second precision, because that needs collection of multi-years data in order to produce that level of precision. Data Release 3 in 2022 not only produced highly accurate positions of billions of stars, in addition, it produced data on millions of variable stars. Remember, it's measuring the brightness of the star, not only their positions. It also gave us information about millions of galaxies. Some of those galaxies were very distant, so-called quasars, very bright galaxies, very distant parts of the universe. And because they have essentially zero parallax, because they are so far away, the motion of the Earth around the Sun wouldn't make any difference to their apparent positions. And because they are not stars orbiting the Milky Way, they are galaxies in their own right, they are considered to be fixed objects. So very remote quasars, a whole set of them, hundreds of them, were used as a reference that tell us how the stars are moving. In other words, how the stars are moving relative to this backdrop of very distant quasars. In addition, Data Release 3 gave us information on hundreds of millions of spectra of stars. That meant we have a much better idea of the population of stars within our Milky Way, because we not only have their colour and their spectral type, we also have the spectra themselves. Almost by accident, we also got data on hundreds of thousands of solar system objects, like asteroids, for instance, some of which we knew about, some of which we didn't. The next data release, which occurred in 2024, labelled here F, was a focused product release. What that means is the people doing the analysis took the original 5 years of data and said, well, how can we best look at, for instance, variable stars or solar system objects, or possibly gravitational lenses where distant objects are imaging or lensing the light from more distant objects? And also, what about these crowded regions? They used Omega Centauri, which is a globular cluster, and they decided to analyse what's going on there to give them a better idea of how can we best look at the really crowded regions of the sky, for instance, those close to the galactic centre. So they started refining some of their analysis ready for later data releases. Data Release 4 will be coming along this year, and Data Release 5 will actually include the entire 10-year set of data from Gaia and will be the full data release, but that is not for some years yet. The idea of looking at Omega Centauri, the centre of a globular cluster, that's used in a sense as a proxy for what's going on in the centre of the galaxy. Let's take that particular cluster and see if we can work out the positions of the stars, despite the fact it is a very, very crowded region. Even the Hubble Space Telescope finds it very difficult to resolve individual stars in the centre of a cluster like this. Gaia analysis showed that there are at least 500,000 stars that were not previously recorded because of the precision with which Gaia can look at data like that. And now we've got better analysis routines by using Omega Centauri as a sort of touchstone. It now should be possible to look at the very crowded centre of our galaxy and start to pick out information about what the stars are doing there. If we think about the structure of the Milky Way, this is what we think it looks like as seen from above. There's a large bar in the centre of the galaxy, and there are various spiral arms indicated by these labels. We are in what's called the Orion arm. Sometimes that was called the Orion spur, but now we're tending to call it the Orion arm. So that's where we are located. We are about 8,000 parsecs from the centre, or if you prefer, 25,000 light years from the centre of the galaxy. In terms of how many stars have we been able to look at and measure distances for, Hipparchus managed to look at the distances of 100,000 stars. And although 100,000 sounds like a big number, all of those stars were inside the yellow dot there. In other words, it's very much just our local neighbourhood of stars was probed by Hipparchus. With the higher precision of Gaia, it was hoped that we should be able to extend that distance and look much further into the galaxy. Data release 2 in 2018, looking at the first 2 years of Gaia data, was able to measure the distances of stars out to that sort of radius shown by the green circle. Data release 3, 4 years later, extended that distance considerably. So now we are able to get information about stars out to that second green circle. You can see we've actually gone a distance of order 30,000 light years or so, or about 10 kiloparsecs, which takes us in principle beyond the distance to the center of the galaxy. We're not actually resolving those stars yet, but it's hoped that in the next data release or two, we will be able to look at the very crowded region in the middle of our galaxy. So again, here's an all-sky map. It's not an image. It looks like an image just because we are mapping out with a pixel here indicating how many stars did Gaia find. If Gaia found a lot of stars, the pixel is bright. If Gaia didn't see many stars, the pixel is dark. And that then maps out something that looks very much like the Milky Way and its dust structure, as well as the satellite galaxies of the Large and Small Magellanic Cloud there. But it's not images, remember, it's not maps like this we're interested in, it's the detail of what those individual star positions and star motions tell us about our galaxy. What can we learn when we start picking apart all of the data from Gaia? Well, one thing we can do is simply say, well, we've now got data for many millions of stars with their colours as well as their absolute magnitudes. If we know the distances and we know how bright they look, then we know how bright they are. So now we have a way of mapping out, and instead of simply saying we can give an idea of what we think the luminosity and colour diagram looks like, now this is actual data. Each dot corresponds to a star. So instead of guessing what we think that ought to look like from a small sample of stars, we now have so many millions of stars mapped out that we know this is what the Hertzsprung-Russell diagram, the luminosity colour diagram, looks like. And so we have a much better way of now probing the stellar evolution of stars in our Milky Way. Rather than just taking a small sample and assuming it's representative, we now have the data that tells us how evolution works in our Milky Way. Accidentally, we found a few other things as well. We didn't really know there were many of these out there, but there appear to be some sun-like stars that appear to be orbiting neutron stars. In other words, Gaia has found a number of stars. If we take out the motion of the star around the Milky Way and we take out the parallax that we use to get the distance, we're left with a few stars that appear to be very much like our Sun, but seem to be moving in circles or ellipses that imply that these suns are orbiting something else which appears to be much fainter. The masses involved appear to tell us that we're probably not dealing with black holes, but we could well be dealing with hidden neutron stars. So we now have data about neutron stars, which allows other telescopes to go and take a closer look to see what's actually going on in these star systems. Data release 2 by looking at the positions of stars. Remember, out now to a distance of some 10 kiloparsecs or so, almost half of the galaxy, we've come to the conclusion that our Milky Way galaxy is actually warped. In other words, if we were able to look at it from outside the Milky Way and look at it side on, it wouldn't be a dead straight line. It shows this very subtle S shape because we are living in a warped disk galaxy. We thought that might be the case before Gaia, but now we know that's actually the situation. We've got hints from looking at other galaxies. For instance, this galaxy, if you look very closely, has got a dust lane down the middle, but if you look really closely, you might notice that the dust lane isn't quite lined up with the axis of the bright stars that are in the background. This appears to be a warped disk, and because we've seen this sort of behaviour in other galaxies, we suspected that it might be the case in our own Milky Way. The reason galaxies have warped disks is because they've interacted with other galaxies in their past. Not only can we look at where stars are with phenomenal accuracy, by taking repeated measurements over a period of years, we can see how stars are moving around the Milky Way. So again, if we take out the parallax and just ask ourselves, what does the motion of the stars look like if you ignore parallax, we found that we can map out the positions and motions of a huge number of stars. Some of them are doing what you would expect. You could argue most of them are doing what you would expect. The stars are orbiting around the center of the galaxy. But some stars appear to be in very odd orbits based on their motions that we can determine from the Gaia data. A very odd orbit might be, for instance, instead of the stars going around the galaxy the way most stars are going, some seem to be orbiting the galaxy backwards. And some seem to be in very elongated orbits, going very close to the center of the galaxy and then coming a long, long way out, and then moving close to the center, moving a long, long way out. So-called needle orbits. And by looking at the motions of large numbers of stars, we can start to infer what must the history of the Milky Way have been in order to give us the orbits of stars that look like what Gaia is telling us. We come to the conclusion, when we look at large enough numbers, that we can determine that this idea that the Milky Way is the result of lots of mergers and interactions of other galaxies. We can't determine the family tree precisely, but we've always suspected that the Milky Way has interacted with other galaxies in the past. And the Gaia data is telling us the orbits of stars definitely backs up that idea. We can get an idea of the history, the galaxy merger history of the Milky Way, here plotted with the Big Bang on the left and now on the right. And we think there have been a number of interactions with different galaxies over past billions of years. I'm not going to talk through them all, but it's interesting to note that Enceladus there, the Enceladus galaxy, sometimes called the Gaia Enceladus sausage, that particular galaxy interacted with us somewhere between 3 and 6 billion years ago. And they've been able to determine, from looking at the nature of orbits of stars, that some of the globular clusters that we see in the Milky Way, in a sense, don't belong in the Milky Way. It is thought that some of the globular clusters that we see now were actually brought to us by an interaction with this Enceladus galaxy. Perhaps it was large enough to have its own globular clusters. It merged with the Milky Way, and some of the globular clusters are what we see now. The Sagittarius dwarf galaxy on the right-hand side there, that's the most recent interaction. It might have started a long time ago, some 6 billion years in the past, but the fact that it doesn't have an ending indicates that it is still interacting with us. What does an interaction between one galaxy and another look like? This is not a particular interaction that we can specify. This is just a generic simulation of what might happen if a small galaxy interacts with a large galaxy. You can see the small galaxy is effectively ripped apart, and the stars of the red galaxy get scattered throughout the larger blue galaxy. Scattered, but not completely uniformly. Notice that there is a distinct population of some parts of the blue galaxy now seem to have red stars in them. And that is one way of determining that we have had a merger with another galaxy, is to see stars with a particular chemical composition as told by the spectra, or stars with particular orbits in particular positions within the Milky Way itself. The interaction with the Sagittarius dwarf galaxy is very interesting for a number of different reasons. This cartoon gives us an idea of what we think happened. So if we run this animation, about 6 billion years ago, the Sagittarius dwarf galaxy interacted with the Milky Way and produced a whole load of new stars because of the tidal forces it produced. It then came round again and 2 billion years ago interacted again with the Milky Way, producing new stars, and then again 1 billion years ago. Each time this galaxy interacts with the Milky Way, you can see that some of the stars were left as a sort of breadcrumb trail as the small galaxy tries to orbit the big galaxy but keeps interacting with it. This is interesting for a number of different reasons, not least the fact that one of the interactions of this galaxy with the Milky Way happened about 5 to 6 billion years ago, and we know that would have produced new stars. And our sun was born at about that time. So it is possible that the sun was formed, the triggering that produced the formation of our sun and hence our solar system was the result of the interaction of the Sagittarius dwarf galaxy coming close to the edge of the Milky Way some 5 or 6 billion years ago. So it's a bit of a stretch to say we owe our existence to the Sagittarius dwarf galaxy, but it's interesting to note that that is a quite plausible explanation for why the sun exists. We can see these breadcrumb trails, these star streams of interactions with other galaxies. So here's NGC 5907, and if it's not too clear, let me turn this upside down and make it negative. Now you can see the star streams more clearly. So this galaxy certainly has interacted with other galaxies in its past, and these galaxies have left these streams of stars in their wake. This is Messier 63. At first sight, there doesn't seem to be much going on here, but again, if we turn it black and white, then again, perhaps you can see more clearly, there are definitely star streams looping around the galaxy, indicating that this galaxy also has interacted with other galaxies in its past. We can see that again in this case, perhaps not so distinctly, but there's clearly a whole load of stars outside the disk of this galaxy, indicating star streams due to earlier encounters. Sometimes you don't even need to turn it black and white. You can see that there are definitely signs of interactions between galaxies that are out there. So we can start to build up a picture of the history of our own Milky Way having merged or interacted with some small and some relatively large galaxies, and different populations of stars within the Milky Way, as indicated by Gaia, tell us about interactions with different galaxies in our past. But those interactions haven't finished. We can think about what's going to happen in the next few billion years. The Sagittarius dwarf galaxy is still circling the Milky Way and will continue to do so and will interact with us again. And in addition, there are interactions that we know are on the horizon. There are two that we know about. The Large Magellanic Cloud is going to merge with the Milky Way in about 3 billion years or so. And the Andromeda Galaxy, M31, is going to start colliding with us in about 4 or 5 billion years. We're not sure if that's going to be a head-on collision or more of a glancing blow, but we know there are going to be interactions on these timescales. Let me finish with an epilogue as to what's happened with Gaia. Gaia finished its data acquisition, its 10 or 10.5 years of data acquisition was finished about a year ago in January 2025. And a few months later, in March of 2025, it was put into a retirement orbit, which sounds very genteel, doesn't it? So much better than a graveyard orbit. What they do is basically, instead of having the satellite orbit around L2, they just give it the slightest of nudges away from L2. And as soon as it's away from L2, it's no longer parked at that position. It will then drift and rotate and stay in orbit around the sun, as indicated by the red line. It'll go around the sun with a period which is somewhat different from the Earth's period around the sun, but in another 10 to 15 years or so, Gaia might come close to us again, but it's been positioned such that it will never be a threat to any other telescope operating around the L2 point. As it moved away from L2, it was actually bright enough to be imaged, and some amateurs actually picked up this collection of dots here in this S shape. Basically tells you about the path of Gaia as it moved away from L2. And maybe it'll be back in another 14 years or so. Maybe it'll be bright enough to image again. The final transmission from Gaia, well, the people on the ground decided to put some fake data into Gaia such that its last transmission ended up looking like that and giving a final farewell message from Gaia to the people of Earth. There will be telescopes coming online in the not too distant future. They will not be replacements for Gaia, but the Nancy Grace Roman Space Telescope, for instance, will be launched hopefully next year. It'll have a stupendous field of view. Compared to the Hubble Space Telescope, there's the pillars of creation from the Hubble Space Telescope, and by comparison you can see the field of view of the Nancy Grace Roman is absolutely vast, bearing in mind it will be at the same resolution. So imagine images with the resolution of Hubble, but 100 times bigger. The Nancy Grace Roman will be able to produce some phenomenal images, and it will be able to produce some data on the positions and distances of stars. But it won't be able to produce anything like the volume that Gaia has produced. Just like Hubble would take thousands of years to map the whole sky, even with a detector this size, it would take the Nancy Grace Roman too long to try and map all the stars in the Milky Way. But it might be tasked with looking at some of the objects that Gaia has looked at to try and complement the Gaia catalogue. Gaia hasn't in itself changed our understanding of the way the Milky Way works. Gaia has produced data, shed loads of data. Data release 4 will be something like 500 terabytes of data. Understanding doesn't come from a piece of hardware. Understanding comes from what do we do with the data. The data that Gaia has produced, with a bit of thought and perhaps a little bit of help from some AI tools, we can use that data of what are the stars, where are the stars, what are the star colours, what are their spectra, how are they moving. We can figure out and we can make models for if the stars are moving like this, then that tells us about the Milky Way dynamics and the Milky Way history and its evolution over the last 10 billion years or so. By looking at the stellar information that Gaia has produced, the colours, the spectra, the spectral types, the mass, the ages, etc., we get a much better handle on stellar evolution within our own Milky Way. By accident, by looking at the data, we also pick up information about neutron stars and black holes, and we also pick up information on solar system objects and by accident some exoplanets. When we get the final data releases from Gaia, there will be so much data from the full 10-year package, and with such precision in terms of distances, motion, dynamics, etc., we should be able to use all of the data in the final Gaia data package that will allow us to get a better handle on not simply how the stars are moving within the Milky Way, but because we have got so much data on how the stars are moving in the Milky Way, we hope to be able to get better data on how dark matter and dark energy might be distributed throughout our galaxy. Two words that have described Gaia in the past are obscurity and ubiquity. Obscurity because, unlike most other space telescopes, a lot of people haven't heard of Gaia because it's in a sense been overshadowed by its cousins, the Hubble Space Telescope and the James Webb Space Telescope, which are able to produce such fantastic images. But if you put obscurity to one side, we have ubiquity, because Gaia has produced data, lots of data, that is going to be used for decades to come. In the next 10, 20, 30 years, Gaia data is going to be used by every ground-based telescope, every new space telescope. It's going to be used by astrophysics research projects for the next quarter of a century. Its legacy will live on. Thank you very much.